All right, so here we go. So now we're going to be talking, we're on to chapter 4. Today we're going to talk about max and mins. It's actually not too bad of a concept, but it's important that we understand how to go about it and attack it. So this first definition that I'm going to give you is about absolute max and mins. And that's important for you to know. So an absolute maximum is going to be the highest point on any graph or function that we have. The absolute minimum is going to be the absolute lowest point on any graph or function. Okay? These values, when we talk about max and mins, I'll be addressing them as extreme values, or sometimes you'll hear me talk about them as extrema. Extrema is just the plural of extreme. So that's not too bad. Let me make sure this thing is on do not disturb. Okay, now the other one that we're going to talk about is also relative or local max. That's important for you to talk about, and local minimum. And I'll draw pictures so you guys can see the difference between the two, because I think it's important for you guys to be able to understand that. But local max and min, or what they're called relative, and the reason they're called relative is because it's something that is next to the things by it. Does that make sense? So relative is you're comparing that value to the things to the right and to the left of it. Does that make sense? Okay, one person. All right. So here, let me show you an example. Again, we're going to go with my favorite friend. F of x is equal to x squared. And now we know how to take the derivative of f of x, right? The derivative of f of x is what? Good. So we know that the derivative of f of x is going to be 2x. And so what we're going to see here is by being able to find the derivative, I'm going to be jumping the gun here, but it's worth jumping the gun. Where the slope is 0 is going to be an important number. So if I go to graph this, right, if I were to go, okay, here's this, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, here's this function, right? We know that this value here, at this point right here, is going to be a minimum, right? Would you agree?
Yeah.
Okay, that's important. Now, one of the things, though, is when we talk about absolute max and mins, one thing that's important is that we're typically talking about something in a closed interval, where relatives are typically talked about in an open interval, but I'll delve into that in just a bit. We know that this point at 0, 0 is the absolute minimum of this x squared function, right? So this is an absolute minimum. One way to figure that out if we didn't have the graph would be to look at the derivative and set the derivative equal to 0. So if I go 2x is equal to 0, I know that we have a x0 is going to be what we call a critical number. And I'm jumping the gun here quite a bit, but it's important for the discussion to become complete for me to jump that gun a little bit. So I know that something important is happening when the derivative is equal to 0. Okay? That's important. Now, from our derivative, we can test that critical number. And this is something that's going to become a big, big deal in this chapter. So when I plug into the derivative, a number that's smaller than 0, what sign am I going to get? Okay, so you're probably a little bit, it looks like you guys are a little bit confused here. So look at this. Think of it this way. What's a number smaller than 0? Any number you want.
-1.
All right, -1. Cool. So if we take -1 and plug it in here, what are we going to end up with? A -2, right? So anything to the left of 0 is going to get a negative sign. That's what I'm trying to say. If I plug in any positive number into that derivative, what am I going to get? Don't I get a positive? Do you guys agree with that or no?
Yes.
Okay, so I'm going to get a positive, right? So when I get that positive there, what this is telling me, and I'm going to explain this to you guys so you guys totally get it. What's the derivative talk about for us in this class? What have I told you the derivative is giving us?
Slope?
It's the slope. What's the slope of all of these guys before I get to 0?
Negative.
They're all negative slopes. What about on this side?
Positive.
They're all positives. At 0, though, the slope is going to be 0.
None.
Right? It's going to be a 0 slope at 0. So I'm going from a negative slope to a 0 to a positive slope. So what that tells me is that this has to be a minimum. Right? Now, this thing here is going to be an absolute minimum. But something important for you to know is that every absolute minimum is also a relative minimum. Okay? Now, not every relative minimum is an absolute minimum. But every absolute is a relative. Does that make sense? I know it's a big concept to start the morning with, but does that make sense? Yeah, I can do it one more time. So every absolute is a relative minimum. So every absolute is a relative, but not every relative is an absolute, max or min. Okay? Now the reason that this is an absolute is because it's the lowest point, right? The reason it's a relative is because if I look just to the left or just to the right, are those values higher than 0, 0? Yes. So relative to the numbers next to it, it is the lowest value. So any absolute, not any absolute, my mistake. And I'll talk about that in a second. So I'll fix that. Not every absolute is a relative either. I'm glad I thought about that. And I'll address it in just a bit. So hold tight to that. If you can compare to the left and right, then it is a relative. But we'll get to that. Okay? So, geez, I can't believe I said that to you guys, leading you wrong. This one is both because I can compare left and right. So here's how I want to talk about this. Relative is relative if I have y values to the right and to the left of our lowest point. That's the best way to talk about it. You have to look to the right and to the left to be able to talk about relative. Does that make sense? That's probably a better explanation. Okay, let me show you something. So this problem that we have here, x cubed, and I'm going to go, instead of to 4, I'll go to 3. I don't want to go with too many values. So if I go -1, -1 is going to give me 0. 0 is going to give me 3. 1 is going to give me 2. And 3 is going to give me some crazy value. Let's see. Oh, here's 2. And then 3 is somewhere out here. So it's going to look something like this. Oops. This will help explain all those things to you right now. So I just found these values by plugging in -1, 0, 1, 2, and 3. Okay? Now, when I go to label it, what do I know about this value right here in terms of the function on the closed interval? What would I call this value right here? Is it the lowest value for this closed function? Of all the values, is that the lowest y value?
Yes.
Yes. Since it's the lowest value, it is going to be the absolute minimum of this whole thing. Now, here's where my mistake was before. This is not relative because it's an endpoint. And the reason it's not relative is, how do I compare a value to the left of this? Can I?
No.
Since I can't compare a value to the right and left, it cannot be relative. Does that clarify that for you guys? Okay, good. So it's only absolute, it's not relative in this case. All right. What about this value? This one right here.
So relative.
It is a relative what?
Medium point to a high point.
It's a relative maximum, right? Because compared to values to the right and to the left of it, it is higher than those values, correct? We okay with that?
Yeah.
Okay. What about this one here?
Relative minimum.
This is a relative minimum. Notice, it doesn't have to be higher or lower than the values for the whole function, but compared to the values of the function next to it, they have to be either a max or a min. So this one is a minimum. You guys with me? All right, and what about this one up here?
Absolute maximum.
That is going to be an absolute maximum. Does that clarify it?
Yes.
Yeah? Okay. Just making sure, because it's important you guys understand that. Yes, relative and local are one and the same. I typically use relative instead of local, max or min, because I like the name relative, meaning compared to the things next to it. Local is just saying, like, local is just in the area around it too, but I think relative is more the comparison word. Does that make sense? But they are one and the same. Evan, does that make sense? All right, cool. Okay. Now, here is the theorem for the extreme value. This is an important theorem. And the critical piece to it is really when we talk about extreme values, the absolute max and mins, we're going to be talking about this kind of an interval. What is this kind of an interval? It's up above it. It is a closed interval. So when we talk about absolutes, we really should talk about absolutes in terms of a closed interval. So really by this theorem, this is a relative min because we're not in a closed interval, but we actually know that it's the lowest value. But by the theorem, it's supposed to be in a closed interval. Does that make sense? Okay, so watch this. I wanna show you a picture so you guys can get some ideas. All right. What did I do here? Okay, so here's my closed interval function, right, with these critical points. What is this?
An absolute maximum?
That's an absolute maximum because it's the highest point, correct? Okay. What is this?
Absolute minimum.
Okay. It is an absolute minimum.
Well, it could be both since it has both ways.
Correct. Very good. It's an absolute minimum. It's also a relative min because I can compare to the left and right. Does that make sense to everyone? What is this?
A relative maximum.
Very nice. This is a relative maximum. It isn't an absolute because it's not the highest, but it is a relative. And then, what about this?
I'm more confused on that one, to be honest.
No, that's the whole point. That's why I did it. It isn't relative, right? Because I can't compare left and right. And since it's not absolute, this is not a dang thing. It's nothing. It's nothing. Okay? And that's important that you understand that because the endpoints on a closed interval can only be absolute. You should write that down. The endpoints on a closed interval can only be absolute max or min. They will never be relative. Understood? So endpoints cannot be relative max or mins. They are restricted to absolute max and min. Good? We're okay? You guys are being really quiet today.
Yeah, I'm good on this, thanks.
All right, thank you. All right. Fermat is my homie, and that's the thing that I was talking about that I showed you earlier. Fermat's theorem tells us where we have a critical number, if the derivative is set equal to 0, if we have a derivative at a specific number and it's equal to 0, then we have a max or a min, or local max or min, or relative max or min. That's what Fermat's theorem tells us. Fermat he was badass. The guy was a badass. So, let's use Fermat's theorem and see if we can use it. Okay? So we have this function, f of x is equal to x cubed, right? Now, let me read this to you guys exactly right so you can understand this. It says, if f has a local max or min, so the condition is, if there is a local max or min, then, and the derivative exists, then that derivative must equal 0. Okay? So the converse doesn't work, and I want to show the converse not working. So if I take the derivative of x cubed, what am I going to get?
X squared.
Okay, 3x squared. And then if we set that equal to 0, I'm going to get x squared is equal to 0, or x is equal to 0, correct?
Yep.
So then when I test that, because I want to test it, just to check the slopes, because that helps with Fermat's, what happens if I plug in a value that's negative into 3x squared? What sign do I get? Any number you want to plug in. We're going to get a positive, correct? Now, if I plug in a positive number, I'm also going to get a positive. So this tells me that the slopes are always going to be positive, right? So when I go to plug in, here is the x cubed function, right? The one thing that we know, and this is kind of interesting, I really didn't draw it very well. Cube should look like this, right? It should be more dramatic. The picture should be more dramatic. I'll fix it. I want to make it so it looks better for you guys to understand. I didn't make it sharp enough. I gotta fix it. It's more of a deliberate turn, right? So what we're saying here is, if I look at this, I know that the derivative at 0 for this is going to be a 0 slope, correct? That's what this tells me, right? When x is 0, right? When we got x is equal to 0, the slope of this was a 0. Agree? Yes or no? Okay, but we see that even though that's a critical number 0, the slopes, there's no way that that's going to be a max or a min, because there's a value relative to it on the left is smaller, and to the right it's bigger. Do you guys agree with that? And so it's not going to be a relative max or min, because it isn't the smallest value next to the things by it, and it's not the biggest value next to the numbers to the right and left of it. So this is a neither case. But Fermat's theorem says if we do have a max or min, then the derivative must be 0, if the derivative exists. So going back to this example here, we saw, look, we have a derivative equal to 0, right? This is the function. It has a max or a min. So at 0, the derivative, since it exists, it must equal 0. Because, and this is the important thing about what Fermat was saying, if the derivative is equal to 0, what is the slope at that point?
Zero.
It's 0. And 0 slope means we have a horizontal line. And if we have a horizontal line, are we getting bigger or smaller at that point? Or are we staying the same? That's right, we're staying the same. So it's important that we remember, I'm loading you guys with a lot of information today, I know. It's important to remember that the derivative is a rate of change, right? So if the derivative is 0, at that specific point, we have no rate of change. And if we have no rate of change, that causes some concern, and so we need to test and see, do we have a maximum or do we have a minimum? Are you guys tracking with me okay? I'm just worried because I can't really see your faces and you guys are so quiet. Okay. All right. So this is important. This is something you should know. A critical number of a function f is some number c in the domain of the function such that two possible things can happen, okay? One, the derivative is equal to 0 at that number, or the derivative doesn't exist. That's what makes something a critical number, okay? Those are the two conditions that make a number critical. Okay? So let's look at this. Now, here's another important one. It says, if f has a local maximum at c, then c has to be a critical number. So if at c we have a max or a min, a local max or min, then that has to be a critical number. And if it's a critical number, it's going to fall under one of these two conditions. Does that make sense? This builds on this. Okay? Should I show you an example so it's not so theoretical?
Yes.
Okay. So let's look at this problem here. I'll graph it. So we're going to be slightly off at a half. 1 at 2 we're going to be -3. And then at 4 we're going to be off the chart. So this function is going to look like this. Okay? It's in a closed interval. Since it's in a closed interval, we know we can find absolute max and mins, right? Right? Now, just to mess with you, if I, on an exam, said, find me the max and mins, and I gave you an open interval, could you find them? You cannot. So you won't be able to find absolute max and mins if it's an open interval, right? That's the extreme of value theorem. So just be aware of that. So in this case, we can find max and mins, and we end up with some critical numbers, right? So let's look at this and see. Let's use the calculus that we're doing now. So my function was f of x is equal to x cubed minus 3x squared plus 1. Well, that should be a plus 1. That's terrible. If we take the derivative of this, what am I going to get?
X squared minus 6x.
3x squared minus 6x. Very nice. And then we can factor out a 3, and an x, so we're going to get x minus 2, correct? Okay, so then that tells me x is equal to 0 or x is equal to 2 are critical numbers. Right? Do you guys agree that those are critical numbers? How do I know that? How do I know that they're critical numbers? Because I set the derivative equal to 0.
Yeah.
All right. Now from here then, I want to test this. I always want to get in the habit of doing this. I want you all to test this. And then here's 4, and here's negative 1/2. Remember, these are included. So when I test it, I'm going to show you. I could plug into this derivative here or here to test a value here, right? Like I could pick like a negative 1/4 and plug it in and see what I got. Do you agree? Because this is for the derivative, this line that I'm using to test. Okay? I could plug in something between 0 and negative 1/2 here to see what sign is going to fall here. Or, better, I could just look at the slopes here. What are the slopes from negative 1/2 to 0? What would the tangent slopes be? They would be positive, so I know that this is positive. What would the slopes be from 0 to 2? Again, I'm looking at the picture. From 0 to 2, what are the slopes? They're negative. Is there anyone that doesn't understand what I'm doing? Please be honest. It's my job to explain it.
Negative.
Does everyone understand it, or do you need me to explain what I'm doing?
No, I get it pretty well.
Okay, good, good. All right, and then from 2 to 4, what's the slope?
Positive.
Positive. Now, again, I'm jumping the gun here, but it's okay. I don't care. Where it changes slopes, I can determine if it's a relative max or min. So in this case, this is a positive slope, right? So it's going up. Here it's going down. So what do you think is happening at 0? It's going to look like this, right?
Yeah.
So what do you think 0 is? What kind of relative is it?
Minimum.
Minimum?
Maximum.
It's a maximum. Because look, this thing that I'm doing here, positive slope 0, negative slope, is this piece. Positive 0. See how right here is that 0? Is right here. That is a relative maximum. Right? Okay. If we look at this one, it's a negative slope 0, positive slope. What do you think that is? What's happening at 2? Is it a max or a min?
Minimum.
It's a minimum. We can see from here I'm going down and then up, down and then up. And so that right there is a relative minimum. You okay?
Yeah.
All right. Now, I want to find some values because let's say that I didn't know that they were relatives and maximums. I want to confirm, right? So pictorially, the numbers that I have to worry about whenever I'm doing this closed interval, I always want to check the endpoints, and then I also want to check the critical numbers. This is the habit that you should get into always. Okay? Out of negative 1/2, if I plug that into the original function, the y value that I'm going to get is 1/8. Okay? When I plug in 0, I'm going to get 1. When I plug in a 2, I'm going to get a negative 3. And then when I plug in 4, I'm going to get 17. Okay? Those are the values, these values from plugging into the original function. Okay? So I know that this is 1/8, 1, negative 3, 17. Make sense? I'm trying to show you multiple ways to do this. So what do I know about f of negative 2? Is it an absolute max, an absolute min, a relative max, a relative min, or nothing?
Absolute minimum.
So this is an absolute minimum?
Oh, my bad. No, that's not.
What would this be then?
Not a dang thing.
That's it. It's nothing, right? We'll call it a nada. All right? What about f of 0?
Relative maximum.
It's a relative max by looking at the picture, right? I've already shown you how to do it without a picture. So when you do it this way, the only thing you have to do is test the endpoints. It saves you time. Here you have to graph and then compare. F of 2 is? That's a relative minimum, correct?
Yeah.
Do you all agree?
Yes.
What is f of 4?
Absolute
maximum.
Perfect. This is an absolute maximum. Now, something interesting to tell you. F of 2 was a relative minimum, right? But isn't it the lowest point overall?
Yeah.
So the best answer for this one is absolute minimum, because it is the lowest point. That's where taking the derivative, we don't know. We would have to test the points for their values to see that it's the lowest point. Does that make sense? So even when you do it this way, you're going to have to do this to check for the absolutes. Okay? If you have the picture, you can just look at the picture. But if you use Fermat, you have to pick those critical numbers and find out what those values are so that you can go about it. Does that make sense?
Yeah.
Would you like me to give you guys one to try?
Sure.
All right, so here we go. Find everything that you can find. All right, let me know when you're ready. Is anyone like lost where you're like, I don't know what to do?
We're supposed to find the maximum and local minimums and of all like the points, right?
Correct.
Okay, cool.
Are you guys ready for me?
Yeah, I think so.
Okay, so the first thing that we want to do with this problem is via Fermat, right? We want to take the derivative. So if we take the derivative, I'm going to get f prime of x is equal to 6x minus 12, correct? And now that I have that, I want to test to see where that is equal to what? Zero, right? I saw Gerardo say it, but he's muted or something. So then 6x minus 12 is equal to 0. And we see that x is going to be equal to 2, correct?
Yes, 2.
So now we want to test that. Here's 2. Here's my 3. Here's my 0. And I want to test some value in between 0 and 2. What's a nice number?
1.
1. So if I plug 1 into this, am I going to get a positive or a negative number?
Negative.
So this will be a negative. And if I plug in some number between 2 and 3, let's say 2.5, into this, what am I going to get?
Positive.
So what does that tell me at 2? What does that tell me about 2?
The local max.
The minimum.
We know that this is, it lets us know that this is a relative minimum, but it doesn't let us know if it's a absolute minimum, right? So from here, we still don't know if this is an absolute minimum. So what do we need to do? We need to check the three values. So I need to check what f of 0 is, what f of 2 is, what f of 3 is. Correct?
Yeah.
Okay, so what is f of 0?
If the 0 is F.
What is it?
-12.
It's 5.
Yeah, if the 0 is 5.
It's f of 0, not f prime. So you got to see what you're plugging into. When I test the points, I'm going to test in the original function because I'm trying to find out what the actual y value is. Does that make sense? What's f of 2?
-15.
Let's see. F of
-7.
-7 is what I've got. What is 3?
-4.
-4. Now we have our three numbers that we need to look at. What is f of 0?
5.
No, but in terms of max and mins.
Oh, I see. Maximum?
It's a maximum. It's an endpoint. So it has to be the absolute maximum. Does that make sense? Okay, what about 2 at f of 2?
Absolute minimum.
That's an absolute minimum, right? What about f of 3?
Should be nothing, right?
That's exactly it. This is nothing. Because it's not an absolute, and it's an endpoint, it cannot be a relative. Make sense? All right. That is 4.1, max and min values. On the homework, I gave you 10 problems like that for you to be able to work out. Okay? And then I'm going to give you 10 problems on 4.2 that I'm about to go over right now. Are you guys ready for me to move on to 4.2?
Yeah, I'm ready.
Anyone needing to write anything down? Just making sure. No? We're okay? All right. Off to 4.2. So this is actually going to look very similar to what we just did. But there's two theorems that are big. There's Rolle's theorem, which is this one that I'm going to talk about. And then there's a mean theorem. And Rolle really is just a special case of mean. Okay? But I'll talk about them both. And then you'll see it and understand. You guys ready?
Yeah.
Okay. So Rolle's theorem has three conditions that are important. Number one, it's got to be continuous on the open interval. On the closed interval. It's got to be continuous on the closed interval. 2, the function has to be differentiable on the open interval. That should be a lowercase f, by the way. I don't know why it's an uppercase. That's significant. So this should be a lowercase f, okay? And the third point is the values, the y values at the endpoints have to be equal. meaning f of like A has to equal f of B. Okay? And I'll show that to you guys in just a second so you guys can understand what happens. If these three conditions hold true, then we know somewhere in between the interval of A to B, there's going to be some critical number C that has a derivative equal to 0. Does that make sense? Okay, so let me do an example. So let's say I give you f of x is equal to x squared, and in the interval from -2 to 2. Okay, so I'm going to go 0, 1, 1, 2, 2. And this is my function that I'm concerned with, right? Agreed?
Three.
All right. Question 1. Is this continuous from -2 to 2?
Yes.
Yes. The three conditions for continuity hold true. Does f of A exists? Does the limit as I approach A exists? And are they equal to each other? And obviously it's over the interval, right? So yes, that holds true. Is this differentiable on the open interval? The answer is yes. It's a polynomial function, and polynomial functions are differentiable everywhere. Right? That's all chapter 2. And then 3, is f of -2 equal to f of 2?
Yep, it is.
So all three hold true. Since all three hold true, then it says the derivative should have a critical number where the derivative is equal to 0. So I'm going to take the derivative, set it equal to 0. So I'm going to get 2x is equal to 0. So x is equal to 0. So this is the critical number where the slope is going to be 0.
0.
Now, I'm going to come back to this and explain to you how this is just like the mean value theorem. But this is all Rolle's theorem is saying. If the endpoints are equal, doesn't matter how many squiggles you have in between, there's going to be at least one point in between the interval where the derivative will equal 0. Does that make sense?
Mm-hmm.
All right, so watch this. Here's mean. So the mean value theorem tells us if these two conditions hold true, then this third condition should happen. So look at this. It says if this function is continuous on the closed interval and is differentiable on the open interval, then there is some number c in the interval that the derivative is going to equal the slope of the endpoints. Does that make sense?
Yes.
That makes sense? Okay, let me go back to Rolle's to show you that it is in fact the same thing. So the slope of these endpoints right here is going to be what? What's the slope of that?
0.
Sweet. The slope of this is 0. Right?
Mm-hmm.
And the slope of the endpoints is 0, so the slope of the endpoints from mean on this one would be 0, correct?
Yeah. Correct.
That means that the derivative should equal what?
0.
And guess what? This one says if the endpoints are the same, y value 0, the derivative must equal 0. Rolls is just the special case of mean. It's the more useful case, actually, in my opinion. Want me to show you mean in a different way so that you can better understand? Here we go. So let's say that I gave you the function let's say I gave you the function f of x is equal to x cubed minus x on the interval from 0 to 2. Right? Is it continuous? Yes, it is. Polynomial functions are continuous. Is it differentiable on the open interval? Yes. From chapter 2, we know that polynomials are continuous everywhere, correct?
Right.
This is where you have to remember your chapter 2 stuff. And then 3 says, then the derivative should equal the slope. Okay, cool. So let's find the slope. Okay? So the slope of this thing is going to be f of 2 minus f of 0 over 2 minus 0. Agreed? And f of 2 is going to be 8 minus 2, so that's 6, minus 0 over 2 minus 0. So I'm going to get 6 over 2, or 3, as the slope of the endpoints. Agreed?
Agreed.
Okay. So I'm going to take the derivative, and the derivative of this is going to be f prime of x is equal to 3x squared minus 1. Right? So mean value tells us to find the critical number that has that same slope. I need to take the secant slope and set it equal to the derivative, correct? That's the third condition. That's this condition here, right?
Yeah.
So I'm going to say, okay, fine, no problem. 3x squared minus 1 should equal what? 3.
0.
Not 0. 3. Because what was the secant slope of the endpoints? Does that make sense, Gerardo? Yes?
Yes.
Okay. And I'll show you a picture of it just so you guys can see it also. So I'm going to get 3x squared is equal to 4. X squared is equal to 4 over 3. So x is equal to plus or minus 2 radical 3. Right? So 2 over radical 3, or we could write that as equal to plus or minus 2 rad 3 over 3. Right? Do I need to worry about the negative case, though?
No.
Why not?
No, it's not in the interval.
That's right. It's not in the interval, so I don't need to worry about it. So it's important that you understand that it's the endpoints that matter in this problem. So I'm going to graph the function just so you guys can all see it. So what this function looks like, just so you know, it looks like this. Now, if I were to go to the other side, just so you guys can see it, it does this. But I don't care about anything left of 0. I'm just showing it to you guys so you guys can see it, okay? Just because the secant slope that matters to us is from red dot to red dot, correct? That's what mean is addressing. Agreed?
Mhm.
So red dot to red dot, boom, 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 boom. What is the slope of that?
So positive.
It's a positive slope, but we already know it. What is it?
3.
It's 3. Right?
Mhm.
Now what's cool is at 2 radical 3 over 3, and I'll tell you what that number is specifically so you guys can have it. 2 times 3. This as a decimal is 1.1547. So 1.1457 is somewhere about, no, I want to get that right. Is that right? Yeah, that looks right.
Yeah. 1.1547.
1.1547, correct?
Mhm.
So somewhere around here, if my picture was right, the tangent of that would have a slope of what?
Same slope.
A slope of 3. Now, the reason I wanted to show you on the negative side, because it says there's 2 possibilities, is if my interval was bigger, at a negative 1 point something, obviously my picture's not right, the slope there would have been also 3. See if I can draw that one right for you. It's going to look something like that. Does that make sense?
Yeah.
So what the mean value is telling us, is if you take the endpoints of your interval, you would get this slope situation. Now, something about it, just because I don't want to confuse you, this, oh, dang, bummer. Silly old me. The reason the slope is 3 is because of the endpoints, those 2 red dots. Okay? If I had gone to find the value on the left-hand side, the endpoints would give me a different slope. So you want to be careful, and I don't want to confuse you with that. So it's the endpoints that matter to give you the slope to find it. Right? Now, what's cool about roll is roll takes you to where it's going to be something useful in terms of max and mins. So if your endpoints have the same value, you know that somewhere in between there has to be a max or a min. Does that make sense?
Mm-hmm.
The mean value tells us we can definitely find a slope that's parallel to it along the way. Okay? Do you guys understand the difference between the two? Roll, the derivative is equal to 0. Mean, the derivative is equal to the endpoint slope. That's the gist of it. Okay?
See.
All right, so let's do an example. So suppose that f of 0 is equal to negative 3. And f prime, so the slope is less than or equal to 5 in that interval. How large, what is the largest possible that f of 2 can be? We don't know the function. We just know a point and some slope in the interval, right? So here's something cool that we can do. Ready? So we know y minus y1 is equal to m times x minus x1. This is point slope formula, correct? So we know that f of 2 minus a negative 3 is equal to some slope. Well, what's the biggest slope that we have possible?
2. Oh, 5.
5. The derivative gives us the slope, right?
Mm-hmm. Yeah.
And so the reason I got this, does everyone know how I got this formula? Or are you confused with how I got it?
I'm confused on how you got the numbers for that.
So here's where I got it. Remember, mean value tells us that f prime of some critical number c, right, is going to be equal to the slope of the endpoints. Agreed?
Mm-hmm.
So I'm going to go f prime of c times b minus a is equal to f of b minus f of a. Okay? Well, what's the c that we're looking at specifically in this problem?
2.
We're looking at 2, right? So I'm trying to find out, all right, what is the derivative at c of b minus a, right? My b minus a is going from where to where? Where are we starting?
Zero.
We're starting we're ending at 2. We're starting at 0. How do I know we're starting at 0?
What's negative 3?
What's this? F of 0, the 0 is x, is equal to a negative 3. So it's telling me I'm starting at 0, and we want to find out what the heck is happening at 2. So our endpoints are 0 to 2. So that's where I'm trying to find my secant slope. Is that starting to connect it for you?
Yes.
Okay, what's f of 2? That's what we don't know, right? This is what we're trying to solve for in this problem, correct? So if we want the largest possible slope, right? Because if we want the largest possible value, we're going to have to use the largest possible slope, right? And what's the largest possible slope?
5.
It's 5. So now f prime at c is 5 times 2 is equal to f of 2. But what is f of 0?
Negative 3.
Negative 3. So I'm going to go 10 is equal to f of 2 plus 3. So what is f of 2 equal to?
7.
7.
7.
Does that make sense?
Yeah.
So see how I use means theorem to be able to get the solution? Now, if I
So
had
kind of like solving, or
go ahead.
is it kind of like solving implicitly for like dy of x when we do it in the other problems? This time we're just solving
Well, no.
f of whichever number.
No, what we're doing is we're making the connection between the derivative and the secant slope is all. So it's the derivative equal to the endpoint slope. And so in this case, because it was the largest and I gave you this, now if I would have changed this to like this, right, as my slopes, the largest possible that I would have picked would have been 5. What would have been the smallest one?
2.
I would have wanted to use the 2. Because remember, slope, the derivative, is the rate of change. And so if we want a slow rate of change, that's going to give us a lower value as opposed to a high rate of change. Does that make sense?
Yeah.
For sure I'm going to ask a question like this on the exam. So you should understand this problem. Okay? Alright, let me show you something else that's cool. This theorem says that if f prime is equal to 0 for all x's in the interval from a to b, then f is a constant on the interval from a to b. Well, let me just show you this as a picture, and it should make a lot of sense. So if I have a constant value, that's crooked. Sorry. That's better. That's better. Okay. If the derivative is 0, what is the rate of change in your y values? What does a 0 rate of change mean? Are you growing? Are you getting smaller?
It's the same. It's not moving.
It stays the same. So that means that my line, whatever my line is going to stay the same for its y values. Its y values are not going to change. And if the y values are not going to change, whatever I choose as my y value will always be my y value. So this is going to be f of x is equal to whatever the constant is that I decide to use. Agreed?
Agreed.
So what this thing is telling us is if the derivative is equal to 0, no matter what x I pick, the function has to be a horizontal line. Does that make sense?
Mm-hmm.
So if the derivative is 0 for no matter what x value, I have a horizontal line. That's what this theorem is telling us. Cool?
Cool.
All right. One last thing. That looks creepy. Can't have that. Okay, that's better. Now, this one is saying this, and this is important. If f prime of x is equal to g prime of x for all x's in the interval from a to b, then the difference between the functions is a constant on the interval. No matter where you are on the function, there's going to be a constant difference between the two functions. That is, f of x is going to be equal to g of x plus some constant c. Does that make sense? Do you need a picture?
Sure.
Okay.
Sure.
So if I gave you this, so it was f of x is equal to x squared, and gave you this, and this was f of x is equal to x squared plus 5, the gap anywhere, the gap here to here is 5, correct?
Mm-hmm. Yeah.
The gap here to here is 5. The gap here to here is 5.
Oh, I see.
The gap here to here is 5. The important piece, though, is to understand, and actually I should call this one g of x. Call this one g of x. Here's the important piece. F prime of x is equal to what?
Prime of
2x.
It's equal to 2x.
G prime of x.
What's g prime of x?
What is
2x?
2x?
2x. Do you see that their derivatives are exactly the same?
Mm-hmm.
But when I go to their function, the distance between the two functions is the constant that is different between the functions. The important piece here, this is what it's telling us. When you take the derivative, what happens to all constants?
Zero.
They go to 0, so they're dropped. Right? What this is saying is there is a family of functions that have the same derivative. The only difference is a constant. Does that make sense? Because I could have had x squared minus 5, x squared minus 1,000, x squared plus 5 million. Their derivatives are all going to be 2x. Does that make sense? The gap is always just the derivative. So if I gave you something like, okay, f of x is equal to x cubed plus 7x squared plus 5x, and then I gave you g of x is equal to x cubed plus 7x squared plus 5x plus 10. The only difference between these functions is the constant. Their derivatives are going to be the same. The way that they move forever is going to be the same with a gap of 10.
10.
See how powerful it is? Once we know a parent function, all the other functions follow what the parent does, except for a difference in constant. Pretty cool, powerful tool. Are we okay with that? Okay, I'm going to stop recording.
Got it.
I'm going to stop recording here and then see if you have any questions for me, okay?